Hello.
Hello.
How are you, Marco?
Good. How are you, Oscar?
I'm good. All good. How is it in Baltaura? Better day than in Barcelona or running? Also rainy?
It's rainy. It's rainy. More like we're inside the cloud, actually. Not coming down. It's just hanging in the air. Sorry, I don't know if the microphone was close enough.
That's fine.
But yeah, it's a lot of mist. We printed some valves, like the respirators, in these few days. But I know that someone is doing that also downtown, probably Eugenio from Nomena.
How are you holding up?
It's good.
Yeah.
Pub Academy aside, everything is good.
Little by little, man.
So today is about data storing and input devices.
Yeah, more input devices and stuff. Yeah. Well, we'll see. Well, I'm recording. I started recording. And I'm gonna start also sharing my screen. Hi, Zoe.
I have a
Welcome.
first question.
Yeah.
Do we need an ESP for this?
No.
Okay.
No. Are you asking because you saw the code in the repository?
Yes.
Okay. No, that is as you will see, it's just a dummy sketch. There's nothing relevant in that you cannot do with any other microcontroller. Okay. So things for this week. I'm gonna start sharing my screen again. So desktop 2, share. Tell me when you see it.
Yeah.
Let's go here. Okay. Let me log into GitLab. Okay. So, as you know, last week or last time I created this Code Club repository. It's on the GitLab Barcelona project documentation. It's an internal repository group in which we put projects that we do in our academy. If you want to check this year, you can go to the 2020 branch and you will see what we have been doing. The first class about Python basics, the Python internet, there was 2 classes actually, and then sensors and DSP. That will be today. So you can clone this repository or you can download it. If you clone it, you can keep the updates. What we will see here today is basically this. The idea is that for the session, we will try to understand a little bit the basics of DSP and signal processing in 1D, meaning 1D is just one signal that has one number after the other, let's say, but it's not 2D like images or videos. Then we're going to try to understand a little bit how to sample, stream, and log data. And finally, we're going to start doing a little bit of data handling in 2D. All this, of course, in Python. Last week, we talked about stuff on the same stuff, and we introduced the same repository, but mainly focused on Arduino, because it's part of the FAC Academy main core. But now we will talk more about Python. So let me go to the theory part very briefly. I don't want to bother you much with here. I would like to jump more into the codes, but you also have documentation in the class repository, in the Code Club interfacing with hardware. And here I call this session interfacing with the real world. Here you have also the link for the GitLab repository. So the main thing we're going to do is that we're going to try to interact with hardware. And generally, and almost all the
Can you
hardware.
quickly share that link on the GitHub, please, to the chat?
Yeah. Where is the chat in here? More chat. Here. So that is here, and then the link is this. Okay. So surprisingly, the needs that when we handle sensor data, generally sensors or traditional scientific equipment that uses or reads sensors has not been mainly focused on high performance. So it's not something that you have to read very fast. And we use this type of protocol or for communication that is called serial. We will see in the networking and communications week what's the difference between serial and parallel. But basically, serial is just for now a type of communication in which the data comes one by one and forming a queue instead of it being sent in parallel. So in parallel, you could think of a very similar type of connector like this, but are generally mainly more intended for displays and this type of things, in which you need a lot of data to be sent at once because you want, for example, a screen to refresh the whole screen all at once, and you don't want each pixel to be updated one by one. You want the whole thing to be refreshed. So the type of protocols that we use are going like serial, in series, or for short serial. You would probably have seen this connector in some equipment. This is the RS-232 connector, which is the main standard for serial communication in the, let's say, traditional PIC or like interfaces with hardware. But nowadays you don't see these things anymore because now what you see is USB. USB, all the ports that you have on your computer are basically a faster, smaller, and easier to handle implementation of a serial protocol. But in the concept is the same as this one. The only difference is that it's a little bit more, well, now it's extended everywhere, and that is a little bit smaller and is a little bit faster, or quite much faster. What are we going to use for this class? So not very surprisingly, if we're going to do serial communication, we're going to use a library that is called PySerial. PySerial is it's able to interface with a lot of different types. If you check the documentation, you will see that it not only has USB ports, but also you have different TCP, single port, many other things, but we are going to mainly focus on USB because it's what all your Arduinos and many of the sensors that you will use, or many of the boards that could hold sensors will use. So very quickly, I don't want to spend too much in here because this is already quite simple. To install it is pip install PySerial, and then to import it, just import serial. We will see in the examples. Now in the actual code, we will interact a little bit more with it. Any question till here? This is all the theory that I have for you. There's nothing else in the documentation that you need to know at the moment. Do you have any question? No? Okay. So if I go to the code club, so I'm gonna show you my terminal. Do you see my terminal there?
Yeah.
So this is the repository. I am in the branch 2020. If you want to change branches in a local repository, you do git checkout and then the name of the branch. So for example, I just switched to master, and you see that in here this change. Now it's not 2020 anymore. Now it says master. In the master branch, there is nothing. I just decided to divide the different years in different branches. If we go to 2020, you check out 2020, then you see the different folders. And the content for today is in the folder called 03 Sensors DSP. Here you will see that there's a file called environment YML. Let's have a look at that. So here is basically everything you need for the class today. If you do conda create environment from this file, there are instructions in the README. You can install it and run. This is based on my current configuration in my computer. So I have given this class a couple of times already, and it should work. But if it doesn't, please tell me so that I can fix it and others can use it. Okay. Probably there can be some problems with versions. You see that here we are installing different packages like Jupyter notebooks or pip or Python 3.7, which is what we're going to use. And they have versions, and maybe sometimes the versions are not exactly the same for all platforms, or they are not correctly specified by me. So please tell me if it doesn't work. If you go to the GitLab repo, let me show you. In Code Club, you see in here getting started, and here you have all the everything that you need to do to have this up and running. So you can create the environment with this code. If you don't want to use the terminal, you can use this Anaconda navigator, so the visual interface, and create the environment by importing the YML, and it will install everything. And then you will have to run the Jupyter notebook. Last week or last time we were talking a little bit about Jupyter. We will talk a little bit more about it today. I think that it will be the main tool that we will use from now on, because it allows us to do more interactive stuff. And also because mainly, I mean, it's not perfect, but I like working on the notebook myself. So since I like it, we will use it. So I go to Sensors DSP. I'm gonna activate the environment, which I call like that. And then I'm gonna open the notebook. So you just type Jupyter notebook, and you see that it creates, it opens the browser, and then you see the exact same thing that you have in the folder. So these files are the same as the ones in here. So data, image, sensor code, source, etc. And this is what you see in the Jupyter interface. Okay. So how is this the structure of this is first there's a notebook. Everything that ends with IPyNB is interactive Python notebook. It's a file in which we have some scripts that we can run interactively in the browser. The first one is 1D DSP basics, as we said, then recording data, then 2D image processing. You see that there are more folders. In the source folder, there are some Python functions, scripts, classes that I created, and we will have a look at them later. There's a data folder that has some CSV data that for now you don't really have to worry about. An image folder for our test with the image processing. And then the folder that Arman was talking about earlier, that is a platform IO project. I am using, I was prepping the class this morning with an ESP32. And this class is this folder contains just that, a piece of code for the ESP32 to spit some data through serial. So let's have a look at the first notebook of all of them. And here we're going to talk about DSP basics. So I use also this notebook to give you a little bit more of information about the notebook. So basically, this interface, this file, is what we call a Jupyter notebook, has different cells. So you see here on the left that when I press them or I arrow down, I jump between each of the cells, and the cells can be mainly two things. It can be code or it can be Markdown. Markdown is because, for example, you want to document and you want to put something. This accepts web. So at the end, this is an HTML file. So you could write Markdown in here, and it will render it nicely. So if you want to document whatever you're doing, and it also accepts code. If you want to run a cell, you press Shift Enter, and you see this little star on the left, and then it will run. The order of execution of the cells is put into brackets, and in this case means that I have just run this cell, and it's the first cell that I run of code. If I run a Markdown cell, I modify something and I run it, there's nothing to execute. Here you see on the top right the kernel that we're using. In this case is Python 3. And if this white dot in here is filled, so it's black, then it will be running. Otherwise, the kernel is waiting for you to give some instructions. Some other tricks, interesting things that will help you navigating.
Interrupting, but
yeah.
I have a Jupyter installed because of Anaconda, but how do I start the folder of the project? Sorry for me. So
yeah, no, of course. So you can you can do two things. So either if you are using Anaconda, which I don't have, you can go to here, so Anaconda Navigator, and here in Home, it will say Jupyter Notebook, and it will say Launch in here. And basically, it will open up the browser, and you can navigate to your folder.
No, it's in the desktop, but it's not in the.
But in there you can navigate into the folder. So you can open folders, for example, the desktop or something. Or easier, if you want, is that you go with your terminal to.
Yeah, I think it's better with
everyone, and then you type Jupyter Notebook.
Thank you.
And then that opens the notebook on that folder. Does it work?
Notebook.
Remember that if you install an environment, you have to do source or conda, activate, and the name of the environment that you create. But first you have to create the environment, and then you can run Jupyter in it.
Activate. Terminal source no se encuentra. Ay, qué demonios. conda activate. Sorry.
Oscar, I'm sorry. Could you go over how to activate an environment?
How to activate an environment?
Yeah.
So, okay, the first thing it would be if you already created it. To activate it is, at least in Mac, is source activate and then the name of the environment. So if the name of the environment was, I don't know, Python 3.7, which is an environment that I have, then at the beginning of in the terminal, it will say this. If it has another name, you can, and you don't know it, you can do conda env list, and it will show you the environments that you have. In this case, I have the base environment, which is the generic pre-installed conda environment that it comes, Python 2.7, Python 3.7, and then another one that I use for data analysis stuff. If you type conda -h, here you will have the help. And for example, if you go to conda env -h, it gives you as well how to create, export, list, update, etc. So it's the environment subcommand of conda. If you don't want to use the terminal because you are having problems with your path or something like that, you can use the Anaconda Navigator interface and then launch from there. And you can even activate your environment from within. Exactly.
Okay, so for me, there's no problem with the terminal. I just would like to understand if I have to do this in a directory in the, for example, okay, should I?
So let's imagine that I am in this is my home folder on the right at the moment. Let's imagine, let's see if I have in this environment Jupyter. No, let's source activate smart system. So if I run Jupyter notebook here, yet another instance will open. It's telling me port whatever is open because I have one done already. And here you see this is my home folder. So I have my desktop, my documents, etc. So I can navigate to whatever I want: FabLab, Fab Academy, Journal, Personal Projects, Code Club, and here I am. So I am in the same folder again. The only thing is that I started from my home folder instead of from, in this case, directly from here. But you can still navigate from wherever you want if you know where the project is. If you want to do it with the terminal, you still can.
Okay, thanks.
Okay. So if you want, what we can do if you want to follow better the class, try to run the Jupyter notebook. If you are having a lot of problems, then you can either write me or we can try to solve them if they are somehow easy, or try to debug them through issues or Riot or email, however you want. Okay.
I have just one minor problem, which is I did the git clone of like you put in the GitLab, but I don't think it cloned the tree 2020 or 2019 because the folder is just an empty folder with a.
Yeah, I have the same problem. I forked it and then I couldn't like have.
Same.
But if you do git, so
Check out.
It said I don't have authority.
Sorry?
Sent the screenshot to your private chat probably, but I can send it again to everyone. And this is what's inside the git clone. Sorry.
I did the git clone, but I don't know if it initiated the.
So what you can do is this git fetch or pull the remote branch.
Mm-hmm.
So you could do something like git pull remote 2020 or git pull remote 2019, and that should work. Does it work?
Git pull remote
2020.
all of them separated by a space.
I just did get in the end. I just did the git checkout 2020 and it worked. I think, yeah.
Yeah. Do you see stuff in there?
Yeah.
Okay.
Did you hear this, Arman?
Yes, but I did the pull. It didn't work. I'm fetching now.
Did you do? Yeah, I did the git clone of the link and then did git checkout 2020 and it worked.
Says that I'm up to date with the
But the thing is, I forked it first, so I don't know if it's worked. I forked it and then I cloned the fork, so I'm not sure if it's gonna work.
Well, give it a try. I think it should.
Remote. Is remote 2021 single word or?
It's 2020 and it's in principle. I'm gonna put it in the chat. So it's either git checkout 2020, or if the branch is not there, which I doubt it, git pull remote 2020, and then git checkout. So checkout
to a new branch. I think I switched to the new branch. So checkout.
Yeah, it's also walked in my case, so you have to first check out to the 2020 and then git pull to get the content.
Working.
Yeah.
Yep. Okay. So some little tips in the in the notebook. They are specified here. The first one, of course, that I already told you is how to run a cell. You press Shift Enter, and then you run the cell. It doesn't matter if it's Markdown or code. If it's Markdown, it will render the Markdown. If it's code, it will execute the code that you have in it. If you want to edit the cell, you press Enter. You see that the cell is on the left is in blue. If you press Enter, it turns green. It means that you are editing it. If you want to escape the edit mode, which is where I am now, you just press Escape, and then you can start using your arrows again. If you want to go in, again, you press Enter. You Shift Enter and you run it. Imagine that you want to add one cell above. You can do so in the navigation here, but if you press A for above, then it adds a cell. If you press B for below, then it adds a cell below. If you want to delete, you can press DD and it deletes the cell. So DD and DD. Okay, so that's quite handy. Those three little things are very useful for you to get up and running. Then you can also check, for example, help on one item. For example, you could say help pandas, and you have the pandas help manual in here, and it gives you what it is. We will learn what pandas is in a second. But also, if you put PD in this case, and then you press Shift Tab twice, then it shows you this little handy same thing documentation. If you press it 3 times, then it shows you, no, that's actually Shift Tab, yeah, exactly. So if you press it Shift tab twice, then it gives you this nice handy documentation. If you press it 3 times, but not in my case, it puts it in here, in the very bottom. I guess that it depends on the Jupyter version that you have. So I'm gonna delete this. So what are we gonna do today? We are gonna interact with sensors. For that, we need a library that is able to interact with the hardware. In this case, we already mentioned it, is PySerial. And we will use 3 other interesting libraries that are more for numerical and visualizations. The first one is called Pandas. It's probably the biggest library for data numerical stuff in Python, that is so important that everyone imports Pandas with the same name. So everyone's put PD for importing it. So every time that you see PD, it's also funny in French, I guess, but in Python is Pandas. Okay, so Pandas has 2 main objects. The main one is called series, which is a 1-dimensional array that contains data, and the data frame, which is something is like the Panda series, but with not only 1 dimension, but 2 dimensions. Meaning that we can have data in a Pandas data frame or a Panda series, and it's very handy because it's where we will put our sensor data in. NumPy. NumPy is as a library for numerical calculation in Python. Everyone also imports it as NP. It's part of the SciPy or Science Python ecosystem. And just so that you see how big this is, SciPy in Nature. So if you know the Nature journal, recently SciPy has been published as part of the methodology for data analysis in Python. And the beautiful thing about it is an open source scientific computing library that people has been building on like little by little since I think 2001. You can check it on GitHub, NumPy. And you see that is repository with 13,000 stars and 4,000 forks. So it's quite a big thing. And if you check for Pandas, it's also even more with more stars. It has 22,000 commits, so it's quite a big thing. As I said, it's very powerful data analysis toolkit in Python, and this is why going with something that is not the best. Let's just go for this, and since it's open and we can use it. Finally, what we're gonna use for the plots, it's mathematical plotting library, matplotlib, also very famous. It's a package for making plots, static plots, all the types, many types that you want, which is the basic visualization library in Python. So let's read some data. With Pandas, we can interface with data that we have on a CSV file. If you go to data 1D data.csv, you will see that I have one txt or CSV file with 2 columns, an index and something I call y, which is basically a timestamp and a number, and goes 500 lines. So I'm going to load that into Python. There's a function called read CSV, which just reads the CSV and loads it and puts it in the Python and a pandas data frame. I could see what I have in the first 5 lines of the data frame that I just loaded is called df for data frame in short. And here you have an index, which I did on the 3rd of January at 11 p.m. and the value. I can describe the data frame. It tells me that it has 500 lines or 500 points. The mean is almost 0, has a standard deviation of 2.7. The minimum is 1, the maximum is 1, and the 50% percentile is 0. So let's plot the data frame and see what we have. Well, you already see it in here. It's a sine wave. Okay, nothing very spectacular. We just have a sine wave that goes from -1 to 1. And you see that we have this mean that should be in 0 is not exactly in 0 because we are missing some points in here. Okay, we don't have the same tail on both sides, and that's why the deviation. So the mean is not exactly centered in 0. If we want to compute the mean of this signal as well, we can do so by just simply calling mean, max, or standard. And we will do the average, the maximum of the whole series, and the standard deviation, which is pretty damn close to what we had in here. The maximum is exactly the same. And so you have a question till now, but this is just the basics to set up our session for today. Is everything fine? Yeah, no?
I just want to ask, I guess in the new version of the Panda, they integrated the matplotlib plots into the new version. So I guess you don't need to import it. You're just not sure that you're using the last one.
Well, I'm not using the last one, but in DF, if you see how I called the plot in here, I did df.plot, which is basically plotting from pandas. So it's already using it. But I think it's interesting for you to know at least the name of matplotlib and have it in the reference in here, because if you don't use it pandas and you use something else, then you still you know what you are calling. Okay, so do you want me to go through this part again of filtering, or are you already mastering what we talked about convolution last time?
If you could go deeper, it would be nice.
If I what?
I know you explained that in the last class, but if you could like go deeper, would be nice. If nobody else cares, it would be nice.
It's totally up to you. I'm more than happy to talk about convolution on a Monday afternoon. Rainy Monday afternoon is nice to talk about.
It's romantic.
Okay. Okay, so let's talk about it again. Also because second time probably will be better than the first time. So the main idea that we want to pursue is having some sort of data cleaning technique for our inputs. For so there are a lot of custom functions that we could use, such as filtering, smoothing, exponential smoothing, many rolling average, rolling windows, however you want to call it. But I think that it's important to understand that in math and in DSP fields, there are some generic concepts that we can use, and it's like having a Swiss knife or a Swiss Army knife, I don't know how you say that, that basically gives you a lot more powerful tools than just knowing many independent sort of ways of doing things. And one of them is called convolution. So convolution is nothing else than a mathematical operation. actually is nothing else than doing multiplication and sum and addition. The funny thing is how we do it. So imagine that we have a signal that we're going to call X, that is a discrete signal, has readings for the sake of simplicity, every 1 second. In this case, we have 0 in second 0, -1 in second 1, and so on and so forth. And we want to do convolution with another signal. In this case, we're going to call it H. H is also a discrete signal, so it means that has a certain amount of values, a limited amount of values. And in this case, we only have 4 values that are starting in the sample number 0, in 1, and then a little bit less than 1, and then almost 0, and then almost 0. The operation of convolution is, imagine that we take this function h, or this group of numbers, and we put it so that we are sweeping from left to right or right to left, it doesn't matter at this moment, signal X. And what we're going to do is put it, for example, in this case, under the samples from 3 to 6. And we're going to multiply each of them, each of the number, element-wise. So the number 6 with sample 0, sample 5 with sample 1, sample 4 with sample 2, and sample 3 with sample 3. And we're going to multiply each one of them by the other. So this one times this one times this one. And then the result of that, we're going to sum it. And we're going to put the result of that addition in number 6 of the new signal. Then we're going to move this guy a little bit to the left, 1 step. And instead of starting in 6, we're going to start in 5. I'm going to reach until 2. And we're going to do the same. We're going to multiply 1 by 1, element-wise. We're going to do the addition. And instead of putting it in 6, we're going to put it in 5. And so on and so forth. The resulting signal is called the convolution between the signal X and what we call the kernel or the filter. Why is this interesting? And here we're going to come back to sharing my whiteboard. So imagine that we have our signal again.
We're not seeing the whiteboard.
Sharing is plus, bring your serve window to the front. Why not share? Okay. Are you resume share?
Yeah.
Now? Okay. So imagine that, so that we keep the same notation. This is our signal X. It's a discrete signal. So even if I paint it continuous, but this is basically one, another, and another, and another, and another, and another. So all the way through that. So I have a lot of samples in here. And I'm going to do convolution with another signal that is, in this case, something like, just let's imagine that, for example. And I'm going to do this in blue. So my signal looks like 1 dot there, 1 dot there, 1 dot there, and 1 dot there. Okay. So actually, let's do it so that it fits a little bit better. Sorry.
You put the second function like on the top graph and then have the bottom graph to be the result of the convolution.
Yeah, okay, I will do that. So the second function, imagine quite difficult to draw with a mouse, I'm sorry. Here in blue, so my second function is going to be like this. So I have a point in there, a point in there, a point in there, and a point in here. And I am missing one point in here, right? So here we have somehow this one goes with that one, this one goes with that one. So this with this, this with this, this with this, the same, so that we have the same raster, let's say. And this is now also, this is X and H. So what we are saying that we are doing in here is that, let's put this in green. We are multiplying the first one times the first one. So that is 0 because this is 0. The second one times the second one, the third one times the third one, and the fourth one times the fourth one. And we are, so multiplication, 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 multiplication. We are taking all that together and summing it and put it in here. So that would be, this is, let's imagine that this is 1. So I'm taking this value and this value, summing them basically because I'm doing 0 times that one, this one plus this one, and this value here. So it's somewhere around here. Okay. And then I go, and after that point, I sweep this function and I move it to the right. And I go and I take my function. Oh my God. I take my function and I move it one step to the right. So I am here. And now my function is here. And then I do the same. Sorry, but this is really tricky. So then I take this value, this value, this value here, and this value here, and I multiply them one by one to then the consecutive ones, and I'm gonna put them on the next slot onto this one. So I'm gonna take this one times this one, this one times this one, etc., and I put it. It's a little bit larger, so the sum will be a little bit larger. And then I keep going with all my signal, and basically in this case you are seeing that we're basically summing this value and this value, or this value and this value, and then put it in more or less in the same way. So I'm doing something like basically reproducing more or less the same signal. It's not exactly the same, but more or less something like that. Why is this of interest? So the other day we were saying that if we want to filter a signal, one of the techniques that we could use is take the average of 2 points and put that point, the result of that average, put it in replace one of the points by the average of two consecutive points. So imagine that our signal is not like that, but is something more like something very noisy, like something like this. Okay, so this is basically somehow like a random signal. Let's try to filter it. If I was filtering it like somehow ideally, what I would think that my signal would look like is something like this, right? More or less. Depending on how much I filter it, I could have a more or less smooth transition, but more or less I could think that is something like that. So if I want to do that mathematically, what I could do is say, okay, my filter signal is going to be for these 2 points. For the first and second point, I'm going to take the average, and I'm going to put the average. So the average of these two is here, I'm gonna put it in here. For the second part, I'm gonna take the average of these two, and I'm gonna put it in here. The third one, the average of these two, and I'm gonna put it in here, and so on. So I put this one in here, this and this one goes from here, this one and this one goes around here. And think always that you want to keep more or less the same raster, or the same, when I say raster, is the distance between two points. So this is what I say that is the raster, which is more or less the same as the sampling frequency. So I want to keep the same raster as the original signal, and I want to put what I get, if it's here, the average of this point and this point, I want to put it in here. And the same for the rest. So the average of these two is gonna be, well, in the same spots. I'm gonna put it in here. And then the average of these two is gonna be in here, etc. And then when I join these points, so I have something like that, more or less. Okay, and you see that all the
maps onto the previous sampling.
Sorry?
The average is basically at the beginning of the raster, like we put the average to, like, with the same X of the previous measurement.
Mm-hmm.
Okay.
Yeah, exactly. So, but then I could choose. So I could choose, since I'm making up the new signal, I could choose where I want to put it. For example, as you see, the raster is not continuous here. I did it very badly because this distance here is much larger than this distance here, but you get the point. If I want to, I could do whatever I want with the average. So I have this and this value. I know that the average is here, so I could put it in the middle. And in which case I would do a centered filtering between the two, and I will be creating another point. I could put it in the beginning, or I could put it at the end, and that is up to me. I mean, probably if I was processing this in like after doing a recording, imagine that I take a sensor recording and I post-process the data. So I analyze the files, I would probably be doing in here. But if I am doing in the real time, I would put it in here, because I have no knowledge of what comes after that. I have only knowledge of what I have already seen, but I have no recording of my file to see the future. So I would put it in here and update the information according to what I have already seen. Now, if we think of convolution, or what we have just learned about convolution, and apply to this, basically we've been taking the average of two signals, of 2 points, sorry, and let's imagine that our signal that is better drawn like this at the moment, it's something like that, and that our convolution filter, our kernel, is just this. So my function has a point in here and a point in here. And just for the sake of keeping things, well, actually, sorry. My function has a point here and a point there, okay? So I only have 2 points. This is 1, 1, right? If I put it in a list. So if I do convolution in here, I'm gonna do, let me erase this. I'm gonna be doing this value times this value. So 1 times this one this is the same as just having this value. So I'll have this value here, and then I will sum this other value. So this other value here, I'm gonna take the average. I'm gonna sum both of them. And what I'm gonna do as well is I'm gonna divide by the number of samples that I am using in my convolution filter. So basically I am going to sum 1 plus 1, and that is 2. So I'm gonna take this value, multiply by this one, sum this times this one, which is basically doing the addition of the two, and then divide it by 2, sorry. And what I have is the same as the average, and I will put that in the same position as before. And then I will do the same in here. I will move this one step to the right, and I will do the same, and then the same, and then the same, and then the same. Imagine that my function all of a sudden is not like that, but that is something like this. So instead of 2 points, I have 3 points. So I am going to take, instead of 2, instead of dividing by 2, I'm going to divide by 3. So I'm going to take this and this and this. I know that this is already 1, so I'm going to just keep it like that. And I'm going to sum all 3, so it's going to be somewhere up, I don't know, up there. And I'm going to divide by 3, so it's going to be probably around here, because there are 2 points that are lower than that one, so probably the average would be a little bit lower, so around there. Then this one is going to be probably a little bit like that. Then this one is going to be a little bit like this one a little bit like that, this one a little bit like here, and here. So my signal with this other filter, instead of looking like this, is looking like that. And if you think of it, what we've been doing earlier for filtering is exactly the same as in convolution. The interesting part of it is that you are using the same definition. So if you make a function that gets as an input your signal and the kernel, and then returns the process or the results, which is equal to convolution of signal kernel, then what you get is something very generic that you can use everywhere. The only thing that you need to change is the kernel, and you don't have to re-implement more code for doing different smoothing or things like that. If we change a little bit this function, we could be getting different things. The other day we were talking about exponential smoothing, which is modifying this function so that instead of it being all ones, it's more something like this, with the idea of imagine that we have 3 points, that we are giving more importance to the present, to the actual state of things, than to the past. And that is probably interesting because you don't want to influence your present value or your prediction of the actual value by what happened 10 minutes or 5 minutes ago.
Is 1 the maximum, or it's just like what we're using at the moment?
No, it's what I use at the moment. The important thing to keep in mind, and I haven't been mentioned this that much because it's a little bit more theoretical, but basically, if you have this signal, I'm like, you know already, a sine function. What you want to do with any operation that implies filtering is something that is, you want to keep the same energy. Which sounds very theoretical, but basically what that means is that if you apply a filter that is a lot of ones, let's say 1, 1, 1, 1 for simplicity. If you take that and do the convolution of that versus that, you're going to have a signal that is 4 times larger. And probably smoother, but it won't have the same energy, meaning that it is much larger than the original signal, and you don't want that. That's why we take and divide everything by 4. In this case, the sum of all of them. If you do other filters, then you also have to keep the same energy, and you have to do the numbers so that you don't modify the energy content of your signal, and you keep the same, let's say, the same amplitude somehow. Okay. So you don't see my screen, but you will see it in a second again. So do you see it again?
Yeah.
Okay, so basically that's what we were doing with convolution. And now we're going to talk about doing convolution, but in Python. So if you check in the formulas.py document, you will see that there is a function called a smooth convolution. And if we check the help of that function, remember that you can make your own help for a function, and then it will display it in here. Basically says implement 1D square box filtering on an input signal using padding on both sides of the signal. You have to send a panda series, so an array of numbers, and then the number of points that you want to have on the smoothing. So basically you have to send the signal itself, and then how long you want the smoothing to be. Here you see that there's something about that mentions padding, and this is an important concept. What happens when you are at the very end of the signal? So what happens when you start here in number 8? You start going to the left and you reach till 0. This one, 3, is in 0. You cannot go further to the left because you run out of numbers. What do? Basically, you're saying that everything will go into 3 here. All this, how do we do it? We could do 2 things. We could basically we could ignore it and say, okay, I don't care about that part. My signal is 5 minutes of recording with milliseconds resolution, so I don't care about these numbers. I have a lot of data. Or you could say, no, this data is important and I don't want to lose it. So what I do is that I'm gonna put zeros in my signal. I'm gonna fake it, and we're putting what we call padding. Padding is I'm gonna pad my signal with zeros on the sides so that my filter can run to both ends. And basically you just put fake values on the left, in this case, which are zeros of the length of your filter, and that's it. You could also do something more intelligent, which is instead of just putting zeros, you could put, for example, the average of your signal. You could try to do a regression and try to extend it in vertical like that, and many other techniques depending on your application. But basically that's what padding means. It means that the filter basically will reduce the amount of points or samples that we have, but we don't want that to happen. We don't want to lose information. And then it uses padding on both sides of the signal. So let's first have a look at what it does. So basically it plots both signals in here, I have the original one, and the smoothened version of it is not very impressive because it's basically the same but reduced because there was not much noise to take care about. But if we have a look at the number of samples in both of them, I'm printing the length of the Y and the length of the smoothened Y, of the smoothened signal, and both of them have the same number, meaning that the padding here worked. I didn't lose any information. How did I added that function in pandas? You can basically say in my pandas data frame, I have these channels. I could create another one by simply saying another equal smooth convolution and then send the signal. So dfy and the number. So in this case, I want to do it with, let's make it larger. So 25. And then if I see df, I just added another one, which is y another, and is very similar to this one. I could plot it and say df plot. And there you go. So I have all three now. The y another has 25 points instead of 21. So it's a little bit lower in here because we are doing the smoothing, a much larger smoothing. If I wanted to do, let's try something more extreme. So instead of doing that, I will do y extreme. And instead of that, I do 251. And I plot the whole thing, df dot plot. And you see that the y stream out of the area that I padded is almost 0 because I'm losing all the information of my signal. If I go to the left or to the right, you see here that the effect of the padding is already taking place because here I padded with zeros on the right side and on the left side. And here I'm making these weird things because my filter is 251 samples, and that is very big. So then I have a lot of information that I am wasting somehow. Then let's have a closer look of what the function is actually doing. Let's run this one. MP is not defined, it's because I didn't actually import it. MP is here. There's something on the chat. You can interrupt me if you want. Just say, I mean, I don't check the chat so often.
Okay,
so you
sorry.
can just...
Okay, I want to ask what is the SRC, because I'm seeing like it repeats so many times in the code. Like
Yes,
it's a specific library.
No, it's a folder in which I put my my scripts. So if you see in my screen, you see a folder here, SRC, and here I put different Python scripts, and in them there are the different functions. Like we're using this smooth convolution one, in which that I imported as this one. So from the folder source formulas, import this function. Okay, for this to work in source, in the folder, you need to have this weird looking file called __ini__py. Otherwise, you won't find it. Okay, the Python, let's say module
It should be
handler.
Python package, right?
Yeah, exactly. So the module handler, it's looking for these things in the subfolders. If it doesn't find it, it won't understand that that's a package or a module. So, sorry.
before we go, one quick question. You were saying you add zeros in the beginning and end on your padding. Why zeros? Why not like the
it's a
beginning value? Or
it's a design choice actually. You can do. It depends on your signal, and it will depend on your application. Here we will see that actually I didn't add zeros. In this, I am adding what you see in here. You see it in the graph. The actual padded signal is in red, which is basically doing an extrapolation of the beginning and the end as a straight line, but it doesn't mean that it is correct. In this case, we know that it should be a sine function, but if we don't tell the code to do so, then it won't know. And basically that's just an extrapolation doing a straight line. But you could put whatever you want. At the end it's just a, sorry, it's a design decision for you to analyze this. Does it make sense? Okay. Okay, so let's have a look at what it's actually doing. So in here we have our original signal in the blue dots, and the padded signal is in blue, and then the smoothing signal is in green. Since we cannot see that very well in there, you see here there's a little bit zoomed. Basically, the padded signal and the original signal are basically the same. Here you see that even if we're joining the points, this is a discrete signal. So the points are very close together, and it feels like it's a smooth line, but it's actually joining straight lines together. And here you see the result of the smooth signal. Now, here it says original signal length 500, the window size, in this case, if we are doing 21, 21 is an even number, so an odd number. So you cannot have an integer. So you cannot put 11, so 10.5 on one side and 10.5 on the other. So basically I put 11 and then 11, and that's what this number is. And basically these are the first values, the last values, which is just doing a regression up and down, putting them together with concatenation, and then doing the smoothing by doing the convolution between the first and the values, the original values, and the filter. Okay, so if we try to look at something a little bit more complicated, like these two functions, we have two signals, one that it has a random value on top, and then another that has another sine function on top, which is a little bit faster or with more frequency. Then we will see something more interesting when we actually run our convolution, smooth convolution with different filter sizes, let's say. And here you see that the larger the filter size, from 7 to 31, the more noise that you remove, but also the more information that you take away from your signal. So in the case of the purple signal, you see that this one is much smoother than the green one, for example, but you also lost almost half of the information because the peaks are not as in the original sine function were. The same happens with the sine function. It's losing information as you go with a larger amount of points, but at the same time is much less noise. So also here it depends on your application, what you want to do, and with this basic function or a smooth or filtering function, you have to be careful a little bit of your parameters and you have to give it a try. Then we already talked about this with the exponential. This is another function. Basically, it's a little bit the same. I don't think I really want to extend that much more on this part. But basically, you see here that even there's yet another caveat, that is that we are introducing also a phase on the signal. So basically, we are moving the signal a little bit to the right, and the more we filter it, also we move it more to the right. And the same happens with the super smoothing, or with the other one that is a little bit more noisy. So just to wrap up, and then we can move on. Important when you do signal processing is that not all the noise will be removed, and that you have to be careful with how much noise you remove, because you can remove also your signal. Be careful also that you don't introduce phasing, so that your signal doesn't go displaced to one side. And you need to pad your signal or trim it in case that you want to apply this type of filters. If we want to do something better, we wouldn't write very likely our own convolution filter, but we can use libraries. And for that, you can use SciPy. As I told you, SciPy is a very broadly used package, and they have signal processing packages. And the first one that you see in here is called convolution. But also here they have a lot of filters and quite a lot of crazy packages for you to use. I just want to show you an example about this one. This is what you can get by using the SciPy signal, which is much better than my convolution filter. In this case, I am using what they call filt, which is basically a filter that you apply twice, but you apply it once from left to right, and then from right to left. In that way, you filter twice, but you also get rid of this problem, because in here you are having a phase because you are filtering from left to right, and you are moving the samples a little bit to the right. And if you do the same convolution operation, but from right to left, then you will remove this problem, and you are displacing it back to where you want it. And as you can see, they're doing much better than I am, because the noise actually is much better removed. We are not losing information. We are still at 1. We are not going to 0.5. It's practically the same as the sine function. And in this case, in which we have the random noise, we have quite a smooth signal. We still have quite noisy one, but probably if we adjust a little bit better our parameters, we will find something better. But as you see, the signal is nothing else than just calling this signal.filtfilt, sending the signal, sending the kernel, and the method. If you read the documentation, you will have examples. I didn't have to do a PhD for writing this code. Is all in the documentation and is replicable. So it's not super complicated, even if they're talking about very complex things. Okay. Do you have any questions now? No?
I just want to ask, do you think the nonlinear regression also can do this?
Yes.
Like pi nonlinear regression.
Yes, you could do. You could also do regression on this, basically you could do that.
Well, is it the same, or is it gonna be like losing so much data? Because I know that it's ignoring the offshore like values.
Well, the thing is that if you want to do multilinear regression, in that case, very likely you will have to know, or if you are already assuming that your function is linear, or sorry, it's a combination of linear functions. So, for example, you could be doing a polynomial or adding polynomials or just simple linear functions by themselves. And in that case, you're already making assumptions of your signal, and that might be not the case. So in this case, for example, we have a sine function, which is totally not linear, and maybe it's not the base, not the best. But again, it depends on the application. Okay, let's move on to the next notebook. Here I have also some interesting peak detection and event detection algorithms. I think that is better that we jump to the next one so that we can cover a little bit more stuff. I know that this is a little bit more hard. Basically, what we are doing is same as we were doing earlier, but we're changing the kernel. So we are detecting peaks by using what we were talking about the other day about wavelets and peak detection. So you can use SciPy functions for that. And basically it gives you where the maximum of your signal are. Again, here you see that it's a little bit tricky and the algorithm is not always perfect. And that takes a little bit of expertise and experience to tune these things. I don't want to go too much into detail about this, but I want to give you a couple of guidelines, which are anytime that you're dealing with sensor data, first, remember that the sensor data is not going to be perfect. Second, remember that you're going to have to try a lot of different parameters. It's not going to be something that you get right away from the get-go. So you have to iterate a little bit. And most importantly, try different options and don't try to find a solution that suits you because you want to get it done, but that suits your problem. So try to solve the problem that you have in hand, but don't try to rush it because normally the solutions are not straightforward and they take time. Also, use filters with caution. As we said, you are going to remove information from the signal, so try to be careful. And mainly just iterate, okay? More references are here. You have access to the notebooks and you have access to my email and to Jitsi or whatever if you want to go deeper into this. I basically spend most of my time doing these type of things in Python for sensor data and these things in the lab. So I'm more than happy to talk about this. Do you need a break or do you want to move on?
I'm happy to move on, but down to the others.
Okay. Well, so I will move on. Now let's do actually something with hardware. Now that we learned a little bit about how Python organizes the data, let's actually interact with hardware and make real data, not just a CSV function. So we're going to record data in real time. That means that we're going to need hardware. In this case, my hardware is this. I don't have any sensor attached. Do you see my, yeah, you see my camera somewhere. This is an ESP32, and I have a USB, which is basically serial. Now we know that with PySerial, we can talk with this guy. So we will learn how to do that and also to store the data. First, let's have a look at what we have in the Arduino. What we have in the Arduino is that. So very simple. We are just speeding by serial sine function. Seems that I love sine functions lately. And for simplicity, let's just do it like that. I have a variable x. I do the sine function of that value, and then I increase it a little bit. Then I give it 20 milliseconds of delay to simulate that I'm reading the sensor, and then I go on. So basically, I'm going a little bit faster, but if you need to me to stop, don't hesitate. This is where my code is. It's a platform IO project. So I do pio run -t upload, and it's compiling, linking, all the stuff, sending, and boom, success. So now I can do pio device monitor. Remember that pio and platform IO are the same. So if I do that, and I have it, it's asking me who do I want to talk to. I have my Bluetooth and Smart Citizen Kit connected and the ESP32. So I say number 2. And there's a serial problem. So the baud rate was wrong. As it says here, I'm opening at 9,600, but I was talking at 11, however much that is. I always have problems saying numbers. So I fix it, and there you go. So basically, I am plotting. If we plot this, we will see that this is a sine function. So actually, let's do that. The first thing we're going to do is with what you already have, which is Arduino IDE. It will take a little while to open in my computer, but basically, as you were asking the other day, if you look at this here, tools, ports, this one. So come on. Oh, seriously? Well, we want to use Arduino. I don't know, it keeps crashing on my computer. Give it a quick try. Hello. Starting, come on. Okay. So tools. That one. Well, doesn't want to, so it crashes every time I open that. So trust me, this is a sine function, is what we are plotting from here. Is that a sine function? Could be the sine function. Ignore. Monitor. So I think that I have to flash the serial. One second. Helps me. We'll see what happens. Basically, this data that is coming from here, I have my doubts about it because the sine function should go from -1 to 1. And you see that there are values that are lower than -1 and probably larger than 1 at some point. And I think that basically I have data from the previous iteration in here. Let me just look for something. Device. Serial monitor, not flashing buffer. Well, I think that's from the past, but it's fine. We'll see what happens. So in here, we are going to import many more things, and we are going to import one library that is called Bouquet. Bouquet is Python is a library for data visualization. For those who know about images and cameras and stuff, it comes from the bokeh effect that the cameras have, and that's why the logo is in there. And basically, it's an interactive visualization Python library. You don't have to make interfaces for this week, but it is interesting to start looking at these things, because in some weeks from now, there's an interface and application programming week. And if you want, if some of you are interested about doing visualization of data, you can use this library to make dashboards and graphs and many things. I use it for this class, but also for other things, and is quite well done. So here, there's something new that we didn't use before, and is this percentage. In Jupyter Notebooks, you can have what we call decorators. Basically, these are running special functions in the notebooks. And what this does is that if you load something in here and you modify it on your computer, then it detects the change and reloads it for you, so that you don't have to start over again. It reloads the whole code and adds the new functionality, which is quite handy because you can iterate much faster. So I run that. This is basically just loading different functions and stuff from Bokeh and from my own code. And you see here that Bokeh 1.4 is successfully loaded. So let's have a look at the very basic thing we could do when we monitor sensor data. Imagine that you have your sensor connected to your computer and that you don't have access to Python, and that you want to load data from your terminal. As you see, I could do pile device monitor -v11 and then it gives me the data. I could also call another program which is called screen, and then open my port. And here is complaining because of the speed. How do I specify?
Terminate the screen.
Sorry?
What was the shortcut to terminate the screen? Because I don't know how to do it.
It's a little bit complex, but it's Control-A-K, and then it will ask if yes or no. So you say why.
Okay.
So you open it. It's not that one. It's this one. So Control-A-K, and you say really kill this window, and then yes. Okay.
Cool. Because they took me ages to add. Yeah, it took me ages to.
Yeah. At first, it happens to everyone, I think. So let's have a look. Screen -help. Actually, screen baud rate. Terminal communication. Okay. So basically, screen like that, baud rate. Does that work? No. Control-K. if you want, this is something.
You don't need to write baud rate, you just put the number without anything before.
Okay, you're right. I'm so stupid lately. Okay, there you go. So Control A, Y. Now, if you want to, let's have a looking. Here I have nothing. So I'm gonna show you how to device monitor. So if I run that, I'm gonna put everything that the sensor is sending through USB into my terminal. It's gonna output that the output of that command into my terminal. That is what we call the standard output of a command, which is a command that you run can have one output, and in this case, the standard one is the terminal again. So it's giving me a message. For example, if I say echo hello, it will say hello, because the standard output of echo of that small program is the terminal application that I have in here. But I could redirect that and send it somewhere else with this larger than whatever symbol. I could put it in a text file, for example, hello.txt. And then it doesn't say anything in my terminal, but if I list, I have a file that is called hello.txt. And if I see what there's inside, it says hello. That's what is inside of my file. If I open it, hello.txt, I have hello in there. Okay, so basically what I did in here is that the command is outputting hello, and instead of showing it into my terminal, I send it to a file. And then I could do the same with the device monitor. So if I do file device monitor -v, and then I send that to, for example, log.txt, it doesn't show me in there, but I could open something else, and then I have a file already in there that says log.txt. If I see it, you see here that I have the data. And this keeps refreshing because my port is still open. I haven't closed it yet. This is still running. If I stop it, Control C, exit, here you see that I still have recorded more data and it's still in there. Basically, that's a way in which we could be recording data, but we don't have much information in here. We don't have any timestamp. We don't know what this is. Basically, it's just what the sensor is outputting, and we're putting it into a TXT file. But we can do a little bit better, and that's why we're going to use Python for that. And that's what we use the combination of PySerial to open the port and to send it to a file. Now, how do we send things into a file from Python? In this case, from Pandas. So I'm gonna make up a straight line from 0 to 100 with 0.1, sorry, from 0 to 1,000 in an interval of 1. And I'm going to export that to a CSV file. Very simple. DS is the series. I'm going to export it to CSV. And where do I want to put it? I'm going to do that so that you don't see that I'm lying. So I send it, and that's it. I open, go to data, dummy series class. Here we go. So here I have my dummy series from 0 to 1,000. 1,000 lines, and the last number is 99.9 because I'm going in increments of 0.1 as I put in here. Okay, very simple. Now you know how to send a Pandas series or data frame to a file. Let's go a little bit deeper. Let's now try to open a port from Python. we are going to import the serial module and a function or a module that is tools, and it will list the ports that we have in our computer. In this case, I'm going to make a list with the ports that I have connected, and then I'm going to print it, but I'm going to put something, a little bit more of information. In this case, I'm printing the number. I'm printing just dashes to separate the name of the device that is connected and the description. Whenever you open a port, if you have a Mac, I'm sure that you have the same in your Windows or Linux machines. You go to USB, and in this case, for example, you have here a lot of information. That information doesn't come from your Mac, it is in the device, and you can access it from Python as well. So here I could put this information. In this case, this is the port, and this is URL, blah, blah, blah. And if you have a look at it, is the same that says in here. Okay, the CP to one blah, blah, USB to UART bridge controller. This is what you see here, because everything comes from the same place. So I have 2 ports connected, and now I'm going to open one. So for that, I created a class that I called serial device. And since I have a ESP, I'm going to make an object.
Problem in the notebook, because they give me problems importing serial, and I don't know why, because I have serial installed.
You have installed serial and you have activated the environment.
Maybe it's not because I didn't have the problem with the other notebook, so I thought that the environment is okay. So
Okay.
If the environment is good for the other example, it should be here. So
yeah, so that's a little bit weird. If you do, if you write this import serial, it gives you a problem. But if you do pandas, for example, does it give you a problem?
import. Ay, ¿por qué se hace esto? Import serial. Shift enter. Model not found.
Okay. So then that means that you are not on the same namespace or the same environment in Conda, and that is either not installed or it didn't install properly when you installed it, or that you don't have the same environment. So did you use the terminal to start running everything?
Yeah, I started a terminal to root the notebook app.
Okay, and the environment was activated in there.
Yeah, but I'm thinking that maybe the Conda input class is not the environment. Well, well done.
Okay, because that what could have happened as well is that when you created the environment, probably there was a problem when you installed PySerial, and that it skipped it for a problem in the environment file, and you can install it by yourself, just doing by pip install PySerial with the environment activated. So the sequence would be source activate the environment, and then pip install PySerial. And in my case, I already have it running, so it says satisfied, requirement already satisfied by serial in this environment here. So it should be fine.
The serial P?
PySerial.
PySerial. Serial. Come on, do something. Yeah, it's not. It wasn't installed by some reason.
Okay. So probably the problem is in the. Let's have a look just very quickly to the environment. So environment. Python. So it was not installed. It's not here, I think.
Pandas are the file.
So it's not on the.
Like last.
It's not in here.
Oh,
So PySerial. Okay, I will commit that and upgrade the environment. Thank you for telling me. Okay.
So back to the notebook.
By the way, when you run Jupyter, it picks up the currently active environment, right?
Yeah, correct. But the thing is that in Conda, it depends on your the terminal session that launches that. So for example, I could have, as you see in here, Conda activate, source like that. So I have on my left, I have an environment called Python 3.7, and on the right, I have Smart Citizen Data. So if I do on the right Jupyter Notebook, it will tell me command not found Jupyter, because I am running it from this environment on the left, and it's not visible to Python 3.7 because I don't have it in there. I only have it on this one. Okay. So you could have, that's the interesting thing about environments. So let us know if it works. I'm gonna keep going in the meantime.
Yeah.
So here, if you have a look at the source code, here you have two files. One is serial device, and then the other one is serial worker. These are two Python classes that I have been working on lately for making serial devices for sensors. And the first one basically gives you the main interaction with the device. It opens, it's something like a wrapper for PySerial. And the other one is what we call a worker. And I will show you what a worker is a little bit later. But basically, it's like a little, it's basically a worker. It's like a small part of our computer that we will dedicate to listen to the device, but that we don't want to have all the script, all the Python kernel dedicated to that. We just want to separate a little bit of that kernel to listen to the device. And for that, we launch a worker or we create another thread. Basically, that's what this is, but don't worry, we will have a look at it when it comes to that point. So that serial device class, I can get the device. I have an ESP32, so my object is ESP. And then I'm gonna open the serial device, in which for that I have to plug it in. So like that. So it tells me multiple devices found, please select one. It's the same as platform IO, so I select number 2. And then I have several properties for this. So I can know, for example, what the serial port is. In this case, this has a property, which is the serial port. It tells me that it's open, the name of the port, the baud rate, and more characteristics for the communication, the byte size, parity, etc., etc. I could read already one line from here. So for example, if I do serial port read line, this is basically PySerial stuff. If I run that, I see what I'm receiving. In this case, I am receiving 0.97, and then this is like enter. So it's like the cartridge return character that you have. And for cleaning a little bit that, you have to put some extra stuff into Python. So you can do that and you decode it. You saw that here there was something that this is a byte interpretation. So you can decode it as UTF-8. This is an encoding that you can use for sending strings of data. UTF-8 is a part of the Unicode standard and basically defines how you specify with 8 bits the different characters that you can have. And of course, there are a lot of combinations and weird things that you can do with it, and you have to agree in both sides. So basically, I know that I am sending in that Arduino sends in UTF-8. So I decode it like that, and this byte thing will disappear. And then I can remove R and N. So I could say strip, and then R, sorry, strip N, and then split. And you see, this will make sense in a second. So, no. So here until here, I have a string that contains the value that I want, and then the carriage return and a new line split. These are characters that the serial is sending, and that's why we know when we are saving the data that there's a new line in here. It's not all the data one after another. There's a new line all the time, and that's how we know that there's new data. The Arduino is sending that when it does print ln here. That's why it print ln is sending the data and attaching red carriage return and new line split to the data. So that's why we know there's a new line. If we didn't put this, it will send all the data one after the other. Actually, we can do that and see what happens. So I flash it, and then right away, I'm opening the device monitor. So we'll link it at some point. Okay. Boom, boom. Okay, success. And now I'm using number 2. So here you see the data, and you see that there's no lines anymore. It's all together because we don't have the ln here, or we don't have the carriage return. Okay, that's pretty simple, but when you see the actual outputs in Python, then you have to deal with it. And how do you deal with those extra characters? Well, you strip the new line, and then you could also strip the carriage return. So, well, okay, sorry. I am flashing, so I cannot open that. Okay, so now we have the new values, and you see that now this is correct. That we don't have values below 1 or over 1. That was the buffer from Platform.io earlier that was not flashed. I clean this. and then I have to open stuff again. So I go here, I have the device, I open number 2, still have the port, and now I remove the N character, and I can remove also the R character, and it changes, of course, because I'm reading a new line every time, but I still, and now I have that as a string. So what I could do is int with base 10, so I can, yep, minus 0.12. So this is called casting. I am casting this value into a float and changing the string type to float type. But what I could also do is, instead of stripping the new line or the carriage return, what I could be doing is putting that into a list. And for that, I do, instead of strip, I do a split. And you see that I am putting that into a new list. Why is this that interesting? Because if I do this many times, then I will create a list of the data in Python right away, and I can append the new values to a list instead of having to strip them strip them one by one. I just can start appending to the list. So that's basically what we are doing in the code. I think that the code is a little bit confusing. So I will just go to the interesting part. Here you see the part that we just came up with: the read line, serial port, decode, strip, and split. In this case, I am stripping R and N, and in case I am sending data, for example, that has, for example, various columns. For example, I send one sensor and then tab or tabular space and then another sensor. Then I split it and put that into the list instead of appending them one by one. And basically, when I call the serial device, what I'm going to do is something that is a function that I made that is start streaming, which is calling that famous worker from earlier, which is another class. That class is a class from multiprocessing. It's inheriting from an object that is called, or a class that is called multiprocessing, which is basically doing this thing of allocating different processes so that we can run things in parallel in Python. And basically it's going to run forever and read to the data. So it's going to read one line, and it's going to say what time is it, here, time now, and is going to put that into a pandas data frame, and then whatever it had earlier is going to concatenate all that all together. It's a little bit complex, so if you want to understand the code, I recommend that you have a look at it with like calmly, and you can ask me if you want. Basically, this guy can receive calls or inputs and send outputs, and this process basically is what is talking with the ESP32, is not the main script. You would be wondering, why do you want to do that thing? Because if you want to make a plot like this, which is, you'll see, well, this is cleaning a little bit. This is because the buffer is not clean yet. But if you want to make a plot like this, you see that the kernel here is not running up here, even if there are things happening in the plot, because there's another guy taking care of the plot, and I can still do stuff. This is interesting because otherwise, if I do something and I want to store the data, then every time I have to pause the execution and do something else. But this is handling the plot, and is handling the saving of the data and saving it in this CSV export. If we open this, now is March 30th at 6:07, and here we started saving data, the raster of 0.05 seconds, and it keeps going. This will update every time I open it, and it keeps going until I pause it. So this is all garbage, and I have to clean up a little bit the code to flash the serial device. But here we have the the actual output of the Arduino, of the ESP. And interestingly, we also can put, so we can interact with this plot. For example, I could zoom in some areas if I wanted. I could save a screenshot, or for example, I could add formulas and do operations on top of it. In this case, I could put another function on top of it, which is a convolution as well, and that is right on top of the same function because it's too smooth. But in a second, we'll try to modify the output of the Arduino and see how that affects the output of this plot. So to understand a little bit what's going on, here I define some constants if I want to save it in a CSV or not, how frequently I am gathering data. This is gathering data every 0.005 seconds. And in the plot is showing 1,000 points. And here is the main part of the code. So as you saw, the ESP device has a property that is start streaming. So I start recording the data and put it into a buffer, let's say, with this raster or this speed, and I work on the data so that I can make the bokeh plot and display it all in here. Now you would be wondering, how do you stop these things? So you have a little cell in here that says stop threads, and then if you run that, stops the whole thing, and now you're not storing more data. If we look again at the data, now is I stopped it at 6:10. So if I have a look in here, I have all the data for 3 minutes with 0.05 resolution until 6:10, and we didn't lose any single line, all timestamped with proper location and quite high speed, and we didn't have to worry about files or things like that. So that's the power of doing it with Python. And I understand that this is a little bit more advanced, but what I would like you to do is that you try to run this, try to understand at least the basics of the code underneath it. And especially that if you go to the documentation, you will find a snippet that is a little bit more simple in the documentation that you can try to run, and which will basically do the same, but we'll try to, if I'm not wrong, it will just print what is receiving into the standard output. And now you know what standard output is. It could be the terminal, or it could be a file. And basically you have a smaller data load. So this is like a softer version of what we saw in Jupyter. And either of the two, you can start trying them and see if they work. Just very, before we pause or stop, notebook has this part in here, which is a way to put more formulas into the plot. In this case, we had a function that is cleaning the not the numbers and doing a convolution, but we could put more things, and probably this is a little bit cumbersome, but I don't know. So you could define, for example, if you want to read the data and process it and put it in the same spot, or if you want to read the data and add a new channel but plot it in the same plot, or put it in another plot. So basically, if you read this, basically says that if we run this and start streaming again, I encourage you to make a beautiful interface for this so that you don't have to run the code. But you see that now we have two plots. The first one contains the function with the smooth convolution, and the second one contains the smoothing. Still, we have here the issue with the flashing of the serial monitor. But now you see that we have two plots in here that you could also play a little bit with arranging them, putting them in a dashboard or things like that. Basically, the core functionality is there, and basically is reading the data from the serial plot, from the serial device, put it into a couple of plots that you can use also if you want to test different filters, different functions, and doing the, I don't know, the derivative, detecting peaks when something happens. Imagine that you're reading a microphone and you want to detect when an event happens, or that you're reading a sensor and you want to trigger a signal or something like that. So you could start playing with this functionality here. And again, well, let's leave that working. But again, if you want to stop it, you just run this cell and it will terminate the work. Let's see. Well, that works as well. So if you click in here, it will save a plot. And if I open that, it shows in here. Well, there you go. So you have a screen capture of your beautiful plot with the signal and everything. So imagine that you're doing experimentation and you want to calibrate your sensors. There you go. There you have a way of doing it. Questions? Do you have any?
Not many.
I think the best is that, oh look, the buffer is clean. So what I suggest is that, and we had this problem last year, is that we want to give you so many things that at some point it becomes a little bit difficult to follow, because the concepts that we are dealing with, if we want to do nice things, there's a little bit more of work into it than just the classes. So we can do two things for that. Either we try to do the same class next time as we did with the basics, but next time you are the ones talking more and you tell me what problems you have. What I recommend is that you show me what you've done if you want to work on it, and we try to have a debugging session. And I don't talk that much showing you things. You show me what you've done, or that we keep going as it is, and then you just try to do these things on your own. But I just keep giving you, let's say, speeches every time that we do a class, but from things that are iteratively more complex, but that require work on your side, besides what we do in the class. And again, since this is not something that is, let's say, in the core program of Academy, what I think is best is that you decide. And if you decide well, I mean, that the best is that you guys tell me what you want to do. So you tell me what you want to do.
I enjoy when like you said, you can't really understand live. So I enjoy when you say, this is how you do it, but figure it out yourself after. Because now I know where to look and which package to look at and stuff like this. And I can play. I think if we all did live, we'd all have problems all the time and we wouldn't do anything for 2 hours.
So my only, just to answer to that thing, I think the live thing for you to do it as well, if we were all together in the same room, it will be much easier, because then I can go and I could have Giuseppe or Xavi or someone else go in checking your screen and helping you. But in this setup, it's a little bit complex. So what we cannot do both things in the same class. So we have to allocate one class to give a master's class, let's say, on DSP or on video processing, and then one class for debugging and that you show me. Or we could do no debugging. In which case, well, tell me.
How about using issues? I mean, we can like just creating issues for some errors that we face that we cannot find a solution, for example.
Okay, so how about then, so that would mean that I still prepare the classes the same way. We do the same sessions. I think since we are recording, everything is still comfortable for you to review it if I'm going too fast or if something is not clear. And I'm more than available for helping with this. Especially, I'm also putting a lot of effort into making the notebooks and stuff understandable and that you can get access to them. If you still have access to them and you have access to me. So that I think that could work, but I want you to make use of your time. And if this is not helping because it's too much, then tell me.
I think that these classes are useful even in the parts that we stop and we try to implement a little thing and go a little bit in the back. So remember what is our environment or something in that way. And I think it's helpful when you help me and when you help the others. Was okay. I know you're talking here, but sometimes you have to go back here and go a little back, and it's very helpful because that general things are now more understandable now that we have some baggage and we all have Conda, we have the PIP, we have more things installed and more things installed in our heads because we try to use it. If you don't mind.
No, of course, that for me that's perfect. So the question now would be, is this, for example, this class is too much?
No, I think as a general feeling, these classes are like perfect. It's a nice workflow. It's more of a like spotlight on ways to do stuff. I think the cherry on top would be to have a sort of like list of things that we should be aware of before the class starts. It's like the day before, having a sort of like point out things that we really should be aware of so we can keep.
Okay. Okay, so I will try to get that a little bit make that better, because actually I'm not very good at that. But thanks. I will try to improve that.
I mean, I think
I take it totally.
It's really good
constructively. So then so if we agree, let's do this then. Next, in 2 weeks from now, we will jump into 2D. But before we start the class, we will have something like 15 minutes, half an hour. So that if you want to showcase something that you did by trying with this code. Give it a try, and in these 2 weeks we can even talk and do things together via Riot or email or issues, however channel, whatever channel is easier for you. And then we do a small showcase of what you've done in the first half an hour, solve doubts and anything, and then I keep going with 2D, the same format. Is that good? And do you have has anyone done? I'm gonna stop sharing and stop the video. No, how do you? This has been recorded, right? Stop sharing.